Am I audible to all of you? Just write in the chat box. Okay. So I am sharing my today's presentation slides. Just a minute. All of you see the slide on your screen? Okay. So let's revise. So in the morning class, we already discussed the pipelining, and there are basically two methods of execution of instructions in computer. um, First is non-pipelined execution and the second is pipelined execution. So before we study the pipeline execution, we must understand the non-pipe execution. So we already discussed what is non-pipelined execution, and uh, its execution time is basically more than that of the pipelined execution. So we need pipeline execution in order to execute the instructions more efficiently in the computer. So after that, we discuss the pipeline execution, in which all the instructions are executed in a parallel form. So we need to divide a much more a big problem into or a big task into small subtasks, and execute the small subtask parallelly in the same time. So this is with this we already discussed in the previous class, and we already discussed the pipeline execution. So how we calculate the AI into BI plus CI in the pipeline execution. Here you can see there are many registers are there in between uh, the combinational circuit and there are many registers which are used for storing our data, and finally we got our result in according to this diagram in the R5 register. So this we already discussed how we in the segment 1, segment 2 and segment 3. As in the previous diagram, we have the value of I from exists from 1 to 7. So there is a limit that I value does not exceed from 7. So as you can see here, in the segment 1, we have 7 clock cycles. So A7 and B7 is there. But in the segment 2, this um, A7 and B7 comes in the 8th clock cycle. And in the segment 3, this A7 and B7 comes in the ninth clock cycle. So as we have only 3 segments, so the clock cycle time in the case of pipeline stage is 9, because segment 3, because A7 and B7 stands in segment 3 at the ninth clock cycle. So that is all we study in the previous class. So the timing diagram, which is also known as the phase time diagram, we already studied. Here also you can see that four-stage pipeline is there, in which four segments are there, one, two, three, four. Here you can see, and the clock cycle of 9 from 1 to 9 is also there, and you can see that the task 6 has been performed at the ninth clock cycle. So in the case of pipeline, in order to execute 6 tasks in the 4 segment stage, we need 9 clock cycles. So that we already studied in the previous class. So moving to the next topic. Now there comes a very important topic known as speed up. So this type of numericals based on speed up are very much asked in your exams. So a simple question related to speed up is there. So consider a four segment pipeline which is used to execute six tasks. So basically here the value of k is equal to 4 is given to us, which is 4 as 4 segment pipeline, and 6 task is there. So value of n is 6. So according to the pipeline execution, we already studied that the first task, which is T1, require k clock cycles to complete its operation. Since there are k segments, so the first task T1 require k clock cycles. So here value of k is 4 because 4 segments are there. So T1 requires 4 clock cycles. Now the remaining n minus 1 task means out of 6, 6 minus 1. So 5 tasks are remaining. So the remaining 5 tasks requires 5 clock cycles. So that is 5 tasks require 5 clock cycles. So the n task clock cycle require, this is the formula. This is the formula for calculation k plus n minus 1. So the sixth task clock cycle requires k plus n minus 1. So value of k is 4 and n minus 1 because 6 task is there. So n minus 1 is 6 minus 1, that is 5. So 6 minus 1 is 5. So 4 plus 5 is equal to 9. So 9 clock cycles are required if we are using the pipeline process, pipeline execution for calculation. Just a minute, some more participants are waiting in the lobby. So as you can see, if we are using the pipeline execution, then we require 9 clock cycles. So the similar problem we can solve if we are not using the pipelining. So in the case of non-pipelining execution. So moving to the next slide, just remember this formula in the case of pipeline, k plus n minus 1. This is the formula, k plus, this is the formula k plus n minus 1. You can write down this formula for in the case of pipelining to calculate the speed up. In the case of pipelining, we use this formula k plus n minus 1. Now moving to the next slide. So in the case of non-pipelining execution, so cycles to complete each task in non-pipeline is equal to k, as it is a k segment pipeline. So value of k is 4. So here value of k is 4. For n task, n cycles required. So the n value of n is 6. So basically for n task, n cycles are required. So 6 into 4. So here we got the value 24, means 24 cycles are required in the case of non-pipelining execution. Whereas 9 clock cycles are required in the case of pipelining execution. So speed up is calculated by using this formula, non-pipelining time upon pipelining time. So for n task, we have nk divided by k plus n minus 1. So this is the formula for calculation of speed up. So speed up is calculated as non-pipelining time divided by pipelining time. So the non-pipelining time is nk as we calculated it, and the pipelining time is k plus n minus 1 as we studied in the previous slide. So this is the formula for calculation of speed up. As n becomes much larger than, this is the special case, This is the special case. As n becomes much larger than k minus 1, then we can ignore the k minus 1 because it is very small in comparison to n. So the speed up ratio is s is equal to nk upon n. So it's the value we find out that it is k. So k is the maximum value of the speed up. So all of you understand it? Just write in the chat box so that we can proceed further. Okay. So just remember the formula of speed up. Speed up is calculated as non-pipeline time upon pipeline time, and its maximum value is k. So here the value of k is 4 because it is a 4 segment pipeline. So the maximum value of speed up is here is 4. So moving to the next slide. Now the next topic in pipeline is types of pipelining. So two of there are two popular pipelines are there. One is arithmetic pipeline and the second is instruction pipeline. So arithmetic pipeline are mostly used in high speed computers. They are used to implement floating point operations, multiplication of fixed point numbers, and similar computations encountered in scientific problems. So, as its name suggests, arithmetic pipeline is basically used for calculation purpose. Some operations we need to perform here, like multiplication, addition, division, subtraction, all the operations in the case of fixed point and floating point are been done in the case of arithmetic pipeline. The second most popular pipeline is instruction pipeline. So, as its name suggests, in this, a stream of instructions can be executed by overlapping fetch, decode, and execute phases. These are the phases of the instruction pipeline. We will discuss it in much more detail later of the instruction cycle. This type of technique is used to increase the throughput of the computer system. So instruction pipeline, with the use of instruction pipeline, we can increase the throughput of the system. So let us discuss these pipelines in detail in the next slide. So in the first, we are going to discuss the arithmetic pipeline. So moving to the next slide. So arithmetic pipeline. So pipeline arithmetic units are usually found in very high speed computers. So they are used to implement floating point operations. The pipeline unit for floating point addition and subtraction. So mostly we are calculating the floating point addition and subtraction with the use of arithmetic pipeline. The inputs to floating point adder pipeline are two normalized floating point numbers. So just remember we are inputting two numbers because addition and multiplication can be performed when two numbers are provided or input to the system. So we are the input to the floating point adder pipeline are two normalized floating point numbers. So here a unique word is there, normalized. So normalized number, floating point number are given as the input. Now capital A and capital B are mantisas, and small a and small b are the exponents. Just remember that capital A and B are treated as mantissa and small a and b are treated as exponents. So the floating point addition and subtraction can be performed in 4 segments. So so basically there are 4 steps we are going to perform in order to mm, calculate the addition or subtraction with the use of arithmetic pipeline. So moving to the next slide. So these are the stages or four steps of arithmetic pipeline. So in the case of floating point adder, these are the four steps. So first step is we need to first compare the exponents. Then in the second step, we need to align the mantisas. After that, we need to add obliques, separate the mantisas according to what we required. In the case of addition, we need to add the mantisas, whereas in the case of subtraction, we need to separate the mantisas. And finally, normalize the result. So these are the four steps. You need to remember these four steps for calculation purpose. So let us take an example on the next slide. So here you need to perform the addition. So here you are given that x is given, and here the x is in the form of mantissa and exponent. So here you can see here x is equal to a into 10 to the power a, and y is equal to b into 10 to the power b. So here capital A and capital B are treated as mantissas, whereas small a and small b, which are at the power of 10, are treated as the exponents. So here a is this, and capital B is this. So here small a is 3, and small b is small b is 2. So first step 1, we need to compare the exponents. So here the first exponent is small a is 3 and small b is 2. So we need to compare it. So 3 minus 2 is 1. So our answer is 1. Then the second step is align mantissas. So here you can see that h is equal to 0.9504 into 10 to the power 3, and y is equal to, as you can see, the given y value is 0.8200 into 10 to the power 2. But since the mantissas are different in the question, so we need to first so as the exponents are different, so we need to first compare the exponent. So as one value is there, so as you can see here, in the section of align mantissas, we need to shift one decimal point from 0.82 to here to 0.082, and we can um, the power of exponent is here is 10 to the power 3. So in this step, we here we align the mantissas. So as you can see here, both the x and y value, the exponent value is 10 to the power 3. So now the as both values are aligned, so we can perform the addition operation. So now we can add the mantissa in the step 3. So when we add it, 0.9504 plus 0.0820. So when we add it, we got the value of z as 1.0324 into 10 to the power 3. And lastly, we need to normalize the result. So in the case of normalization of result, so non-zero value. So here you can see that non-zero value comes before the decimal. So normalize in the case of normalized result, this this non-zero value you should come after the decimal. So here you can see that the non-zero value 1, which is present before the decimal in the step 3, will come after the decimal in the step 4. So our answer after normalization is 0.10324 into 10 to the power 4. So this is our final result after the normalization. So by using these four steps, we can calculate the addition, subtraction, and operations with the use of arithmetic pipeline. So all of you understand it, just write in the chat box so that we can move further to the next topic. Okay. Just remember these four steps in the case of arithmetic pipeline. So move into the next slide. So as you can see here in the diagram, the arithmetic pipeline execution. So I am just enlarging it because it is the diagram is just a minute. I am enlarging the diagram so that it can be clearly seen by you. So now you can clearly see the diagram. So here you can see that this is the flow chart for calculation of arithmetic pipeline. So here you can see that in the step one, in this step one or the segment one, first we are going to compare the exponent. As you can see here, the power of exponent means small n small b. First need to compare it in here, then their difference, whatever their difference, need to be aligned in the mantissa. This is the step 2. And after that we need to add or separate the mantissa as per our requirement in the step 3. As you can see here, step 3. In the step 4, all these results are going to save in the register, and finally we need to normalize the result in the step 4 and adjust the exponent, and finally our result is going to be saved in the register. So this is the flow chart for operation or for execution of the arithmetic pipeline. So it's numerical we already discussed in the previous slide. So this is the just uh, just the flow chart or how the execution can be performed in the arithmetic pipeline. So that's all for arithmetic pipeline. Now we are going to discuss the instruction pipeline in the next slide. So moving to the next slide. So the next topic is instruction pipeline. So pipeline processing can occur not only in the data stream but in the instruction stream as well. So as you can see in the case of arithmetic pipeline, we are performing the operation only on the data. Um, but in the case of instruction pipeline, we can also perform this operation in the instruction stream as well. So an instruction pipeline reads consecutive instruction from memory while previous instructions are being executed in other segments. So this caused the instruction fetch and execute segments to overlap and perform simultaneous operations. So these are the stages or the of the instruction pipeline. So a pipeline processor does not wait until the previous instruction has executed completely. So this is the characteristics of non-pipeline processor. But in the case of pipeline processor, we can perform the operation simultaneously. So rather it fetches the next instruction and begins its execution. So these are the introductory part of the instruction pipeline. So moving to the next slide. So in four stage pipeline architecture, the execution of each instruction is completed in following four stages. So here in the case of instruction pipeline, four stages are there, and these stages are fixed. So first we need to fetch the instruction from memory, then we need to decode the instruction of the fetched instruction, and third we need to execute the instruction which is decoded in the second step, and in the fourth step we need to write back the result which we get in the third step to the memory. So these are the four step and it is fixed. So you need to remember it for instruction pipeline. First is instruction fetch, second is instruction decode, third is instruction execute, and fourth is write back the result into memory. So moving to the next slide. So to implement four-stage pipeline, the hardware of the CPU is divided into four functional units. So each functional unit performs a dedicated task. So as you can see here, that four stages are there. So in the first stage, we need to fetch the instruction. In the second stage, we need to decode the instruction. In the third stage, we need to execute the instruction. In the fourth stage, we need to write back the result which we got in the instruction execute in the memory. So this is the output. After write back, we need to place it into the memory. So that's our output. So in this way, our instruction pipeline works. And as you can see here, only one control unit is controlling all these stages. And in between every stage, we have the registers are there in order to save the value and transfer it to the next stage. So all of you need to remember this diagram, which is the working diagram of instruction pipeline. All of you understand it till now? Just write in the chat box so that we can move further. Okay. So moving to the next slide. So in pipeline architecture, instructions of program execute parallelly. So this is the main feature of pipeline architecture. All the instruction can be executed parallelly. So when one instruction goes from nth stage to n plus 1th stage, means if the value of n is 2 and it goes to the 2 plus 1 means third stage, then the another instruction goes from the n minus 1th stage to the nth stage. It means that if the value of n is 2 and it goes to the third stage, then the another instruction goes from the first stage, means 2 minus 1 first stage, and moves to the second stage. That's how in the case of pipelining all the stages are filled. And if one instruction is in stage is in a particular stage, then the other instruction are dealing in the n minus 1th stage, and some other instruction are dealing in the n plus 1th stage at the same time. So this is the main purpose of using the pipeline architecture. So moving to the next slide. Now the phase time diagram. As we already discussed it somewhat in the previous slide, now we are discussing it in detail. What is the use of phase time diagram? So phase time diagram shows the execution of instructions in the pipelined architecture. So the following diagram shows the execution of three instructions in four stage pipeline architecture. So here, as you can see from the diagram, from the phase time diagram, there are four stages: S1, S2, S3, and S4. There are four stages, and in the clock cycle, and there are three instructions. As you can see here, I1, I2, and I3. There are three instructions. So in the stage one, we can fill um, these three instructions in the three clock cycles, means I3, I1, I2, and I3 in the first, second, and third clock cycle. So as we move on in the stage 2, um, and they are shifted. These instructions are shifted to the next clock cycle. So in the S2, in the stage S2, these instructions I1, I2, and I3 are shifted to second, third, and fourth clock cycle. Then in the same way, in the stage 3, these are shifted to third, fourth, and fifth clock cycle. And in lastly, in the stage 4, they are shifted to the fourth, 5, and 6th clock cycle. So as you can see here, in the fourth stage pipeline, uh, this I3 occurs at the sixth clock cycle. As you can see, a sixth clock cycle. So the time taken to execute the three instructions in four-stage pipeline architecture is six clock cycles. So we can calculate the execution of instructions in pipeline architecture by using the phase time diagram, and it is very easy. You need to just draw a table which is a form of matrix, and in here you can write the stages in the row wise, and in the column wise you can write the clock cycle, and the values of this matrix or the table can be filled with the instructions. So you can easily calculate mm, the clock cycles required in the case of pipelined execution. So all of you understand it? How we are going to calculate it by using the phase time diagram? Just write in the chat box. Okay. So moving to the next slide. Now, in the case of non-pipelined architecture, the time taken to execute three instructions would be, as you can see here, n into k. You can remember the formula, as we already discussed in the case in the previous slide. In the case of non-pipelined architecture, um, we get here three instructions are there. So and each instruction is, and we are using um, the four stage pipeline. So value of k here is 4, and the value of n, because we are using three instruction, is 3. So we need to multiply it 3 into 4. So we get 12 clock cycles if we are using the non-pipelined architecture. And in the case of pipelined architecture, we get the value as 6 clock cycles. 6 clock cycles in the case of pipelined architecture. So obviously, pipelined execution of instruction is far more efficient than the non-pipelined execution. This can be clearly seen from the example. Now moving to the next slide. Now comes the other important parameters which we are going to consider in the case of pipeline execution, and many numericals in the exam are based on these parameters. So the following parameters serve as the criteria to estimate the performance of pipeline execution. So first is speed up, second is efficiency, and the third is throughput. So these are the three important parameters on which numericals are based, and there are unique formulas to calculate these three parameters. So let us discuss each of these parameters one by one. So first we are going to discuss the speed up. So moving to the next slide. So speed up means it gives an idea of how much faster the pipelined execution is as compared to the non-pipelined execution. So the formula for speed up is non-pipelined execution time divided by pipelined execution time. So by using this, we can calculate the speed up. So by calculating the speed up, we can find out how much the pipelined execution is faster than the non-pipelined execution. So this is the formula. You need to just remember it. Speed up means non-pipelined execution time divided by the pipelined execution time. So moving to the next slide. Now comes the formula for efficiency. So the efficiency of pipelined execution is calculated as, efficiency is denoted by just eta, then it is denoted as speed up. So first, in order to calculate the efficiency, if we are using this formula, so you need to first calculate the speed up. So efficiency is equal to speed up divided by number of stages in pipelined architecture. So how many stages we are using in the case of pipeline architecture? We need to divide the speed up by number of stages, or we can also calculate the efficiency by using this formula: number of boxes utilized in the phase time diagram. Number of boxes utilized. As you can see in the phase time diagram, some boxes are utilized, whereas some boxes are remain empty. So efficiency can be calculated as number of boxes utilized in phase-time diagram divided by total number of boxes, whether it can be empty or it can be filled. So by using this formula, we can easily calculate the efficiency. Mm. Now moving to the next slide. Just remember these formulas. For efficiency, we have two formulas. Now the third parameter is throughput. So throughput is defined as the number of instructions executed per unit time. So it is calculated as number of instructions executed divided by total time taken. So how many instructions we are going to execute in in total time? So by using this we can easily calculate the throughput. So you need to just remember these formulas in order to solve the numericals based on pipeline. So moving to the next slide. So let us solve numerical based on pipeline. So a question is given to you. You can just remember those formulas because questions are directly come to apply those formulas. So consider a pipeline having four phases with duration 60, 50, 90, and 80 nanosecond. So so duration of each phase is given to you. Means first phase is of 60 nanosecond, second phase is 50 nanosecond, third is 90 nanosecond, and fourth is 80 nanosecond. So given latch delay is 10 nanosecond. Latch delay means the time required to transfer from one stage to the next stage is 10 nanosecond. So you need to calculate these six. Um, um, First, you need to calculate the pipeline cycle time. Then second is non-pipeline execution time. Third is the speed up ratio. Fourth is pipeline time for 1,000 tasks. Then sequential time for 1,000 tasks. And last is throughput. So these six you need to calculate. So you can take a copy and a pen with you and just write the data given in the question, because we will going to solve it. Just take a minute to write down these data given in the question, because we are proceeding to solve this. Now moving to the next slide, I think all of you note down this data in your copy. So now we are going to solve it. So moving to the next slide. So first you need to write down what is given in the question. So four stage pipeline is used. Delay of stages is 60, 50, 90, and 80 nanosecond, and latch delay or delay due to each register is 10 nanosecond. So first you need to calculate the pipeline cycle time. So first is cycle time is equal to uh, maximum delay. This is the formula for calculating the pipeline cycle time. So cycle time is equal to maximum delay due to any stage plus delay due to its register. So out of these stages, you need to take only the maximum value. So max value from 60, 50, 90, and 80. So the max value obviously is 90. So you can take the 90 value and the delay due to register. So 90 plus 10, so 100 nanoseconds. So the pipeline cycle time is 100 nanosecond. So you can use this formula. Maximum delay out of these and delay due to the register. So only 5 minutes are remaining for the class. So no hurry up. So we can calculate it now. The second is non-pipeline execution. So now non-pipeline execution time. So non-pipeline execution time for one instruction. So in the case of non-pipeline, as all are executed sequentially and not parallelly. So we need to add up all these stages like 60 plus 50 plus 90 plus 80. So after that, we get the our answer is 280 nanosecond in the case of non-pipeline execution time. So now we need to calculate the speed up. So speed up, as we know that speed up formula is no, speed up is equal to non-pipeline execution time divided by pipeline execution time. So non-pipeline execution time is here we calculated as 280 nanoseconds, and the pipeline execution time we previously calculate as 100 nanosecond. So the speed up ratio is 2.8. So all of you understand it till now? Just write in the chat box so that we can proceed to the next slide. So we already calculated the three parts of the question. First is the pipeline execution time, second is the non-pipeline execution time, and third is the speed up ratio. Now moving to the next slide. So now we are going to calculate the pipeline time for 1,000 tasks. So pipeline time for 1,000 tasks is calculated by using the formula the time taken for the first task plus time taken for remaining 999 tasks. So the first task will take 4 clock cycles because four stage pipeline is there, and the remaining 999 will take only 1 clock cycle each. So 4 into cycle time. So cycle time of pipeline is 100 as we calculated in the first part, and the 999 into 100 nanosecond. So 400 nanosecond plus uh, 99,900 nanosecond. So it gives us the answer as 1 lakh to 300 nanosecond. So by using this formula, we are going to calculate the pipeline time for 1,000 tasks. So you need to just remember that you can calculate the first task separately and the remaining n minus 1 task separately for getting the answer. Now moving to the next slide. So this is the fourth part of the question. Now these are the last two parts, the fifth and the sixth part. Now the sequential time for the 1,000 tasks means here we are not using the pipeline concept. So non-pipeline time for the 1,000 tasks is remember the formula. We have the formula as n into k. So here we have in place of n we have 1,000. Then time taken for the one task. So one task time taken for one task, as we already calculated the time taken for one task in the case of non-pipeline is 280. So we need to multiply 280 into the number of tasks. So here it is 1,000. So here we got the answer is 2,80,000 nanosecond in the case of non-pipeline architecture. And finally, how we are going to calculate the throughput. So throughput for pipeline execution is equal to number of instructions executed per unit time. So this is the by this we can calculate the throughput means 1,000 tasks divided by 1 lakh to 300 nanosecond. This is by this we can calculate the throughput. So all of you understand it? Just write in the chat box. So we finished. So all the six parts are calculated. So thank you very much. Uh, uh, that's all for the pipelining concept or the pipelining topic in the in unit 5. and we are going to discuss the next topic tomorrow. So thank you very much. Now you can leave this meeting.